First of all, I would like to thank you for attending this ceremony. I want to thank the Hiller family for establishing the Robert J. Hiller Professorship and thank them for their commitment to education and research. The Dean has described the biography of Robert J. Hiller. He brought together the Big Ten and the Pac-10 in the Rose Bowl. And the first Rose Bowl, I looked it up, was 1947 between the Big Ten team and the Pac-10 team. But now we're together in one league for 4 teams. And I want to thank the college for granting me the professorship. Thank you to ECE and the Radiation Laboratory for giving me support in teaching and research since I joined almost 10 years ago. Also, thank you to my students and postdocs for stimulating discussion and helping with research. And lastly, I want to thank my family, my 2 children, and my wife, Hannah, who is here, for their support. My talk is on satellite micro-remote sensing of the Earth and multiple scattering of waves. I'm glad that the University of Michigan has a long, strong tradition in micro-remote sensing with the work of Professor Ulaby, Sarabandi, Tony England, and also Christopher Ruff. I'm glad to be part of this tradition as I move forward. So these are the topics: remote sensing of snow-water equivalent, and then we move to polar ice sheets, soil moisture, and then we talk about vegetation and forests, and talk about how to compute multiple scattering of waves. And recently, we also applied the same concept to photonic crystals, a different area of applications. Snow-water equivalent is important to understand the role of snow in the water cycle. For example, you want to know how much snow is stored in the mountains. And secondly, you want to have resource management in case of water insecurity, and then the effect of climate change, and also hazards of flooding and caused by snow melt. And what is snow-water equivalent? If you have a layer of snow, when it melts, it becomes water. So how much water is the snow-water equivalent? So 1 meter of snow depth will convert to 0.2 meter of snow, so snow-water equivalent is 0.2 meter. What do you mean by satellite remote sensing? Because satellites allow you to have frequent revisit. You have to go to the same place every 5 days, right? Because if you go once a month, then it's changing all the time. So you have to repeat 5 days. And because the space distribution is heterogeneous, you need to have something like 250 meters of resolution over the whole world in snow and every 5 days. So what are the physical principles? As I'm a modeler, so there are 2 contributions to radar backscanning of snow. First of all, the radar will enter the snow and hit the ground, the red color, and give you the rough surface scattering. And the other thing is the inhomogeneous in snow, because if you look at snow, next time you look at snow, it's actually ice crystals, ice particles, ice grains in air, and the ice crystals cause volume scattering, backscattering. And that is why you have 2 contributions, the volume scattering due to the ice grains and the surface scattering. And we have modeled using 2 models, dopally densely packed. On the left side is the densely packed spheres, in which we use the Corsi crystalline approximation way back to calculate the phase matrix and scattering absorption coefficients, and then we put into the dense media radial transfer equation. And the other effort is more new. We computer generate these irregular shaped particles and aggregates, and then we solve them labeled as by continuous medium, and then we solve them by full wave solution Maxwell's equation to calculate phase matrix, and then we again use the dense media radial transfer equation. And here are some results. Remember, there are 3 satellites. One satellite is Sentinel-1, the European satellite, C-band at 5.4 gigahertz. It is very appropriate for deep mountain snow. And these are data taken over the French Alps. And this is the snow and the French Alps map. And I have 3 curves for every figure over 3 locations. The top figure is plotting the co-polarization. That means you shine in vertical polarization, you receive vertical polarization, and you always plot as a function of time. And then the second middle curve is the cross polarization. That means you send in vertical polarization and you receive horizontal polarization. And the third curve is take a ratio of cross pole to copolarization. And you see that the distinguishing feature is that it increases with time. So as you go with time, the cross pole to copole increases with time because the snow depth increases. So this gives you a signature how to retrieve the snow depth using the cross polarization increase as a function of time over the copolarization. Now this is the existing mission of Sentinel-1. And I mentioned earlier, we are in the team of working on 2 satellite proposals. And one is the US one, which is the SNOW group of NASA, and the other is the TSMM, the Canadian mission, and both use the similar concepts. Now, we don't have satellite data, but in this case, we use the airborne measurements and tower measurements. So on the left is the airborne measurements taken over the Trey Valley Creek in Canada and showing the X-band scattering as a versus the model versus the data, and this X-band above and then the KU band below, and the agreement are quite good. And then it's an international effort. So in Finland, we also have the tower measurements, and this is a KU band of 13.7 and then KU band 7.2, a comparison between the model and the experiment, and they are in good, reasonably well, particularly the high KU band frequency. Now, so what we usually do is that we use the simulations, we generate a lookup table, and then we use some sort of regression or training to fit it into some sort of regression model, and then you can quickly use the model to retrieve a snow water equivalent. So again, we only have airborne because it's proposed satellite mission. So we have airborne campaign in Trey Valley Creek in Canada, in Grand Mesa in USA, and then also in Sloyanki in Finland, and also in Austrian Alps. So recently we put agreement between the airborne campaign and the matching of data to the retrieval algorithm. And these 2 proposals, the SNOW group was not selected. It was received very high ranking, but it was not selected, unfortunately. But we are still working on the Canadian mission, TSMM mission. Now, next subject is remote sensing of polar regions. So the idea here is to use passive microwave radiometry between 0.5 to gigahertz. And this is a proposed satellite by our Italian colleague, and they call it Cryo-Red. And this, very fortunately, this proposal was selected by ESA to move forward, phase 0. Phase 0, that means you move forward and then they down select. But this is very fortunate. They were selected to move forward with phase 0 studies. And the idea is to use 0.5 to 2 gigahertz to measure the polar regions. There are 3 types of target area. One is the polar ice sheets, like Greenland and Antarctica, and the other is the sea ice thickness, and the other is the polar ocean salinity. As you know, that the ice melt, the water becomes less salty, particularly in polar regions. But my group is only involved in the polar ice sheets. The polar ice sheets, as long as in this picture here, there are 2 zones. One is the dry zone. In the dry zone, there is firm. And because of falling snow, the firm density fluctuates all the time, causing a lot of scattering and reflections. And below the firm is the ice, and below the ice is the bedrock. How deep are the ice in glacier and in polar ice sheet is kilometers, 2.5 kilometers. And then you want to infer the temperature profile of the ice sheets all the way to kilometer. And this is actually discussed in my undergraduate class. I have 2 undergraduate students here in my class. And I told them that ice has a very small imaginary part, so you can penetrate all the way to several kilometers at gigahertz frequency. And that's why you can retrieve the temperature profile. And then the other thing is that in another region, is the percolation zone. And in this zone, the water melts during the summer, and they drip down, become water body, a mixture of ice and water. And for some reason, they do not freeze in the winter, so they remain a mixture of water and ice. And the problem is that they will cause a lot of problems in terms of mass. So what is our model? As I said, we are a modeler. So Okay, so this is the illustration, okay? So why is it so important? Because this is the polar climate change. And if you look at the loss of mass in the Greenland, it is hard to read, plotting the loss of mass in Greenland, ice loss, from 2000 to 2020, back 20 years ago, the loss of mass about less than 1 trillion ton per year. But up to now, 2020 is 5 times more. So a huge loss of Greenland loss mass. And one effect is the density fluctuations of the firm. And the other is a subsurface temperature profile. The ice is very thick, all the way to 2.5 kilometers. But at the top, it is very cold. At the bottom, it's very warm. It's actually close to melting, 273. So if the basal temperature, the base is 0 degrees centigrade, it will melt. So it's important to retrieve the temperature profile of the ice sheet. And again, we use the 12 channels of brightness temperature between 0.5 to 2 gigahertz to infer the firm densities as well as the temperature profile. So again, we use a model. And the model is a 3-dimensional random media model. We have density fluctuations. We have short scale, long scale, vertical, horizontal variations. And there are some frozen layers of ice that cause reflections. And we use a Fourier transform model of 3-dimensional variations to look at the angular coupling and the coupling between vertical and horizontal brightness temperatures. And on top of that, we will also put in the temperature profile, which is cold at the top but warm at the bottom. So we try to collect this model and try to interpret the data. As I said earlier, this is a proposed mission. There's no satellite. So we have airborne. We have 2 airborne campaigns. One is 2016, and the other is 2017, and this is the aircraft. And the blue dot is the flight, a short flight, a testing flight in 2016. And the red dot is a long flight going over several areas, important areas in Greenland, to measure the brightness temperature as part of the airborne campaign. So using the 12 channels of brightness temperatures, we can compare with the data. So on the left is the compression of data using the 3-dimensional scattering model. And this is plotting the data as a function of 12 channels of frequency. The blue are the data, and red is a model, and over 4 locations in Greenland, and they agree very well. So we include 3 types of reflections: the short scale, the long scale, and the ice frozen layers. So this is the first set to look at the density fluctuations of firm layers. The other is look at what's the temperature underneath the ice, all the way to 2.5 kilometers. So we take this 12 channels brightness temperature over a large regions of Greenland, and we retrieve the temperature profile. And what you do is that there is a model of temperature called the Robin model. And in it, there are 4 parameters marked by the red. So using the 12 channels, you retrieve the 4 parameters, and you can map the temperature profile under the polar ice sheets. It's quite interesting because if you look at this is Camp Century, it is only 1.5 kilometer, not meter, 1.5 kilometer deep, and this is the scale of temperature. This is warm at 270. It will melt if it's above 270, and low is 230. So if you look at Camp Century, it's quite cold at the top, and it's warming up at the bottom. But if you move to Anchorage, it's very dangerous because it's very cold at the top. At the bottom is all yellow and orange. So it is close to 270, and you know that 273 degrees is 0 degrees centigrade, and the ice can melt. So this basal temperature is a very important goal to using the chiral red or ultrawideband radiometer to measure subsurface basal temperatures. Now I talk about aquifer, right? Aquifer, as I said earlier, is a melting of water. It drips down to have an ice-water mixture, and it will cause accelerate mass loss. So we have a model here, and quite interesting at bottom data. This data is plotting the temperature, brightness temperature, the measurements, as a function of time. Now, if you have aquifer, and winter is very cold, and summer is warm, and winter again, it decreases very gradually when there is an aquifer below, a water body below, water ice below. But if there's no aquifer, it just go up from winter to summer and quickly dies out. So looking at a pattern, you can recognize whether there is an aquifer inside the ice sheets. And the aquifer can be very problematic because it accelerates mass loss. And our model is again a random medium model, but the important thing is to look at the refraction of the aquifer. So in the water aquifer and snow interface, there is a contrast, so you have a lot of refractions. So how much is the refraction depend on the direct constant, and which is, I'm glad that the undergraduate students here because we talk about refraction in the undergrad 330 class. So what we do here is that we use a model, full wave Maxwell's equation. We generate this porous medium with water and ice, and then we use Maxwell's equation to solve the real part and imaginary part of the permittivity. Direct constant is plotted as a function of water content, the real part and the imaginary part. The red curve is our simulations. The blue curve is the Maxwell classical formula, and you can see that there are wide differences. That's why we use Maxwell's equation, not the classical model. So you can see that the full wave simulations give much larger than classical mixing formulas, and because of larger contrast, you create a lot more refractions, a lot more contrast between vertical and horizontal template refractions as in our undergraduate class. And in undergraduate, we don't call vertical horizontal, we call it TM and TE, right, with the same name. So using this, we can explain the brightness temperature as a function of time. So there are two graphs here. The upper graph is the vertical polarization, the lower graph is horizontal polarization, and there is a large difference. A large difference as explained by the new results of the direct constant based on full wave simulations. And here is the same thing. So our model compared the time series data very well for both cases. And these two cases, the left one is in Greenland, right? So Greenland has aquifer, but also Antarctica also have aquifer. So Antarctica, the Wilkins ice shelf is also aquifer. So we can explain very well. And then the top two curves show you the temperature profile and how deep the aquifer goes. So in the summer, the aquifer is very close to the surface. As the winter goes, it goes deeper and deeper. And the temperature of aquifer is what? 0 degrees, right? It's water, or 0 degrees. But above it is cold. So you can decide the aquifer is very important in terms of the mass loss. So we can compare with the data very well using this physical model of electromagnetics and apply it to Greenland as well as Antarctica. Now we go to closer. Soil moisture. So in most systems of soil moisture, there are 4 satellites that we were involved in, and Kamal also worked on some of this. One is the SMAP, which was launched in 2015, and US satellite. And then second satellite is a US-India collaboration. US-India has a collaboration, and it's going to be launched supposedly 2025, yeah, hopefully. And then Sentinel, I said earlier, is European satellite. And I don't want to forget that there is a University of Michigan satellite, Professor Christopher Ruff, for the CITNES, measuring refractions from GNS, and they are also interested in soil moisture, right? So it's I can call it a U-Michigan satellite. Okay. So, and then what is the applications of soil moisture? It's very important to talk about earth science. Water cycle, energy cycle, carbon cycles, climate change, flood prediction, the flood here, the drought here, and then the landslides. It's very important for soil moisture. And then what is the basic model? The basic model is you have soil, we have a lot of rough surface, and you do rough surface scattering. And then on the right is the computer-generated rough surface. And then we use a method called surface integral equation, and Eric is an expert on this. And we solve it by the sparse matrix method to get a lot of solutions. And then we use the solutions to compare with the data. And the first data I want to show, the comparison, is a data a long time ago, collected by Shalabanti at ULB. And it's over where? Usulanti, right? Everybody knows Usulanti. And we have four pictures, 4 graphs, 20 degrees, 30 degrees, 40 degrees, and 50 degrees. And the horizontal is a simulation, the vertical is the data, and VV is you shine in vertical polarization, you receive vertical polarization, HH is you shine in horizontal, receive horizontal, VH is you shine vertical, receive horizontal. So all 3 channels of VV, HH, and cross polarization agree quite well. And using that, we build up a table, lookup table. And as I said earlier, if it was very large, so you do some regression to fit some empirical. And then once you have the parameters, you can use all those information to retrieve soil moisture. And we apply in this paper by my colleague in JPL. He applied to the Ypsilanti, Michigan sites, and he agreed quite well. Also applied to the Southern Great Plains in Oklahoma, retrieving for 6 fields. So it's a good for the soil moisture retrieval. Now I go to the recent work on vegetation and forests. Now most of the land is covered with vegetation and forests. So the key question is that can the microwave L band, 0.2 meter, can it go through vegetation and forests? But the idea is how much is VWC, is volumetric weight content. And that's very easy to understand. You go there and cut all the corn and you weigh it and you divide by the area. So the upper limit was 5 kilograms. So the initial map, it says that we cannot see more than 5 kilograms because if it's too dense, you cannot penetrate the vegetation. And 5 kilograms, but then forest excluded because forest, if you go back up, you can cut it and weigh it, it's something like 15 to 30. So you cannot see full forest. So forest was excluded from the mission way back in 2015 when the mission center was launched. But then why is this 5 kilograms? It is based on an old model that was used about 30 years, the radial transfer equation model. In this model, it assumes all the vegetation, the scatterers are uniform, constant density, and that's why using this, you only can see 5 kilograms. You cannot go more. But then when you look at the real picture of forest vegetation, it's not like that, right? You can see that the plants are attached together, the branches are attached to a tree, and there are gaps between the trees. So this old model, giving the 5 kilograms, is being challenged by many people. So what we do here again, because we're in electromagnetics, we want to solve Maxwell's equations. So how do we solve Maxwell's equations? So now you can take this picture here. So this is basically a multiple scattering picture. And if you look at many plants, what you see if you apply the commercial software like finite difference, it will put down many points in the entire space. Say 10 points per wavelength, 1,000 points per cubic wavelength. You put in every point and you solve the finite difference equation, many points. And it's very slow and time consuming. But we want to have a new method. The new method is to use the multiple scattering theory of waves. So if you look at multiple scattering, actually the picture is quite simple. You have a scatterer, how this scatterer scatters to all other scatterers, right? Okay, like this. And then the second thing is that now I'm sitting here, I'm getting scattering wave from all other scatterers. So the fast summation, you have to do it fast, right? Fast summation of the scatterer wave from all other scatterers. So I told my student the 2 keywords of multiple scattering is all other scatterers. So how do you do all other scatterers? So we developed this method, a multiple scattering method. That means we use the T matrix we extract the T matrix of a plant. And given this T matrix, you can quickly calculate the scattering to all other scatterers. And then we use these multiple scattering equations, we just iterate, because what you do here is that you iterate, you scatter to everybody scatter to you, and among yourself, you iterate many times, 10 or 20 times, it will converge. And those are the Goldilocks multiple scattering equations. And the first step is how do you add them fast, right? Because I'm sitting here and all the other scattering to me, how do I add them fast? So we have a technique called the triple FFT. And what you do is that the plants are random on a horizontal ground, but you can translate them to move them into a periodic grid. And then you can use 2-dimensional FFT. And the third dimension is a sort of the order of the scatter wave. It turns out that also translation invariant. So we use a triple FFT and was able to compute the solution fast for multiple scattering problems. So now how do we illustrate it well? So first, we apply to a cornfield. And this is a cornfield of 225 corn plants. There are many cornfields in Michigan. And first of all, we wonder whether our technique is correct. So we do this and compare with FACO. FACO is a commercial software. And it's quite slow, but you get the result. And then our method, fast hybrid method, is very fast. And we plot the field underneath the corn plants. and they are in good agreement, showing the method works very well. And then we are trying to pure realistic case. So in realistic case, you have 225 corn plants, and they will grow. Right? You can go to the cornfield, so we go from 0.6 meter, 1.2 meter to 1.8 meter. As the plant grow, the weight increase, right? From 0.35, 1.09, 1.9, 3.2, 4.4, right? That's why upper limit is 5 kilograms, it's 4.4. And then we simulate the transmission. So there are two kinds of transmission. If you are along this direction, you shine, there are more transmission. If you go this way, there are less transmission. So we simulate this and calculate transmission for different parts of plant growth, because as the plant grows, the VW increases all the way to something close to 4.5 kilograms. So this is our application to cornfield. And then we go to wheat field, right? So wheat field is, we use 160 wheat plants, 70 meter tall, is a wheat field here. And we calculate the transmission using this waste transmission method. We get 75% transmission. If you use the old model, it's only 32%. So solving macro equation help you have more transmission, and they like it because you want to see the soil moisture, and that's why they like our work, and that's why I'm still a NASA team member for many years, because they know that we show better results, and they are encouraged by these new results. But then our emphasis shift, because they want to do forest, right? Because forest is 20, 30 kilograms per meter square. It's not included. So they want to do forest. Why is forest so important? Because 1/3 of the land surface is covered by forest. And the applications is biomass, ecosystem, carbon cycle, deforestation, wildfire monitoring, and landslide monitoring. But forest, as mentioned earlier, is much beyond the original 5 kilograms. It is something like 20 kilograms per square meter. And that's why the NASA's map mission has a new target since 2022 to go to forest. Okay. So now they do a lot of work in forest. So in 2022, we have an experiment in the Harvard Forest in Massachusetts. And the idea is to measure the GPS signals in the forest. You can do it after this talk. You can go to forest and carry your cell phone and measure GPS signal. Okay. And then there's a team of 15 students, and among them, 2 of my students, they are here today, right? Okay. So they go there and measure the soil moisture, they measure the diameter of the tree, and they measure the water content. So, and they have the GPS signal, operate the whole group to measure the GPS signals under forest. How big is the area that we do? So we do an area in the Harvard Forest, 300 trees. How tall are the trees? 70 meter to 90 meter tall. So how big is the area? It turns out about 5,300 square meter. And you go back and measure the football field, it's 5,350 square meters. So it's close to the size of a football field. Okay. So we try to do full wave simulations of 17 meter tall tree, 19 meter tall over an area comparable to a football field. And then we have the results. So here is the picture of all the 300 trees, right? The red color is the oak. The 70 meter, the blue is the maple, and we plot the field pattern under in this square area, 0.4 m. And we find the transmission is very high, it's 70%. So you can have 70% if you don't, you can go and try to get 70% using a GPS receiver. It's much higher than people think in the past. Of course, we also compare with GPS. So over here is a comparison of GPS signal. You can go and compare, right? You can go there, measure, we can compare for you. And it turns out that it's quite good because the peak and valley line up. And also the values, the peak values also line up. That means we believe that this number is still correct. You have close to 70% transmission through forest at L-band, GPS signals, 70%. And because of this, they are very excited, and then the team, the NASA, actually signed an agreement with Malaysia. So we are going to the Malaysia rainforest and measure ground measurements. Now then we have success. So how much CPU we need to do 300 trees? So we run on 3 kinds of software. One is HFSS, very common. And using HFS, using the computer of my group, we cannot do 1 tree, it's too big. But using FACO, we can do 8 trees. So FACO will take 21.3 minutes and 258 gigabytes for 8 trees. But it cannot do 300 trees. But our method can do 300 trees, and it takes us, by my student, John Wu, it takes about, on a desktop, not high-performance computing, 2 hours and 79 gigabytes, and we produce the simulation of the field pattern under the forest. So we are excited by this way of solving multiple scattering equations. So we somehow try to apply to a different area because there are several kinds of multiple scattering problems in devices and so on. So one area that we applied recently is to photonic crystal. So changing the topic a little bit, now going to the inside the lab rather than outside. So photonic crystal is a periodic structure you put in a sort of infinite number of scatterers placed in a periodic manner. And each is a very complicated scatterer, like this structure here. And this is a 2-layer triangular prism in 3D photonic topological insulator from this paper here. And here, the goal of photonic crystal is to calculate the band diagram. The band diagram is plotting the frequency as a function of the block vector. So for each frequency, there can be 5 frequencies. For each block vector, there are 5 frequencies. There are 5 bands. So for each block vector, you are supposed to calculate the 5 eigenvalue frequency, and that will give you the block diagram. Okay. So now we say, let me apply the same method, right? So what is that? Keep on to all other scatterers and summing from all other scatterers. Same idea, right? So now you can use the T matrix. So you use the T matrix to calculate scattering from one scatterer. And using the T matrix, you can get scattering to all other scatterers. And the idea is to shine an instant wave, a family of instant wave on this scatterer, and calculate the family of scatter wave. And by doing this, a scatter wave times instant wave inverse, you get a T matrix. Using that, you can calculate scattering to all other scatterers very fast. The second thing is to add scattering from all other scatterers, right? And you have to do it fast too. So now we have this way. So this is summing scattering from all other scatterers from except yourself. You sum from everybody else, right? Not yourself. And it's to all other scatterers, an infinite summation. But no matter how many scatter waves you receive, that you see, it is only a summation of circle waves, right? Okay, because circle is complete. So you only need to calculate the coefficient of the circle waves. So the idea is to calculate this coefficient of scatter wave, which is summation from many scatterers, infinite number of scatterers. And you have to calculate for many frequencies because you don't know the frequency. The frequencies are known. You cannot specify frequency. So you have to calculate this coefficient very fast for thousands of frequencies. And we developed this method called broadband Green's function. That means you can calculate this very fast for 5,000 frequencies. And then because you sum over to infinity, you have to have fast convergence. So we have an imaginary wave number extraction, the accelerated convergence. So you can compute this scatter wave for many fast over 5,000 frequencies and a fast convergence of the summation. Okay. So using this method, we calculate the coefficient D, and from that we call the small d, and small d just in terms of the big D. And then we put into the eigen equation, because eigen equation tells you search the frequency, the 5 frequency, right? And this eigenvalue, you can source the 5 frequencies for each block vector. And this is quite simple because it is in terms of the D, which is the big D, the coefficients of the summation, and the inverse of T matrix. And we can do it very fast because we already have 5,000 frequencies for each of this. So you just go up, pick up the 5 eigenvalue, 5 frequencies, and you can solve the band diagram very fast. So now we compare. So we compare with the COMSOL. COMSOL is a very common software called multiphysics solution. And this is plotting the 5 bands as a function of block vector. And for all the 5 bands, COMSOL is this, and is very good agreement with COMSOL, which is a standard software for multiphysics simulation. Then you ask how much the CPU comparison. Now this figure is created by 30 points, right? 30 points in the block vector. So for each point, you calculate 5 frequencies. So how much time it takes between the COMSOL method and our multiple scattering method? So for 5 bands using COMSOL, 30 points, 5 frequencies, it takes 3 hours and 33 minutes. But using the method, again 5 bands, 30 block vectors, only 4.63 seconds. So we are much faster than COMSOL. And again, 30 points is not good enough because for those who are in photonic crystal, you need to have all the band values for the first Brillouin zone, right? So the Brillouin zone is a 3D Brillouin zone, and you have 10 values for each component, beta X, beta Y, beta C for the block vector. So you have 10 values each, 10 by 10 by 10. In principle, you should compute for 1,000 block vectors. If you use the COMSOL software, you can take 120 hours. We haven't done that, right? It takes a long time. But we think that our method is very fast. We haven't done it, but we think we can do it. Okay, so summarize that my career has been built around this satellite global micro-remote sensing. I described the existing mission and the proposed new missions. Existing mission, we have satellite data, but proposed we have airborne and tower measurements. And we talk about the importance of solar water equivalent, polar ice sheets, soil moisture, vegetation and crops, and forests. And the applications are important for earth science applications, resource management, disaster monitoring, global climate monitoring. And the basic theme in the modeling is how to do multiple scheduling of waves. So our recent work is how to do it fast, solution of Maxwell's equation. And we apply to these 5 areas: rough surface scattering, dense media, and vegetation and forest. And recently, we also try to do the new work on photonic crystals. Thank you very much.